This lecture is about equipotential surfaces as well as equipotential volumes or regions of space. So I'll start with this example, which you've seen before. For a point charge, the surfaces of constant potential are surfaces of constant radius, right? And in three-dimensional space, surfaces of constant radius are spheres, right? So let's imagine you have a point charge, and as a beginning example, let's consider a point charge Q. And we know that the electric field looks like this, and I'll only draw a part of the electric field line diagram. But this is, there's field lines on the other side as well, right? But the potential for a point charge, I showed you, had sort of this form right here. So if you consider only staying a certain distance away, a certain radius away from the charge, V is constant for constant R, right? So that's suggesting that here are these spherical surfaces. They're spheres in 3D, right? And each of these surfaces is a constant R surface. And if you manage to have a constant R, you're going to have a constant potential, a constant value of the potential. And these are referred to as equipotential, and in these cases, they are surfaces that are equipotential, right? But we can say a little bit more. You notice that V of R, and this is for the case of positive charge, as R is bigger, right? So if you consider going further and further away from the charge, so bigger and bigger radiuses, V gets smaller, right? So V gets smaller as R gets bigger. So that means that if I was to say something about the relative value of the potentials of this part of the surface, this part of the surface, this part of the surface, this would be a lower potential than inside, right? So I'm going from high to low. If I did a negative charge, right? So here's a negative charge. You know that the electric field lines actually, they don't point out from the charge, they point into the charge. So this is the case where Q is instead less than 0, right? So let me flesh out the field line diagram a little bit more. But the potential is written with exactly the same formula. But now, since Q is negative, this statement here is backwards. I'll remind you that the potential for a negative charge, right, so the vertical axis is V and the sideways axis is distance away from the charge, the electric potential is shaped like this. So as R gets bigger, right? So as you consider bigger and bigger R's, right? This is a bigger value of distance from the charge than here. Can you see that at bigger R, I am actually larger in potential than at smaller R, right? This is the high value and this is the low value, right? So it's still surfaces of constant radius, which are the equipotentials, but it's a little bit backwards. You actually are higher in potential further away than closer, right? So it's backwards when the charge switches sign. But I'd like you to notice something that we can take away from this. It's a generically true the field lines point the way from higher potential to lower potential, right? So the field lines, this is just a generically true statement. If you look up here in the top drawing, you can see so in the top drawing, the field line, can you see it's outward, and it is pointing the way from higher potential values to lower potential values. So the field lines point the way from high to low potential, right? And in the second drawing, see the field lines are now pointing this direction, and they are taking me from the high potential surface to the low potential surface. But there's actually something else we can say as well that's related. So if you move in directions perpendicular, right? Perpendicular is the same kind of meaning as transverse. So perpendicular to the field lines, then the potential does not change, right? Let's see if we can see that up here. So if you move in directions perpendicular to the field lines, so this is misspelled, then the potential does not change. So here is the field line, right? And it's pointing inwards in this case. And if I move perpendicular to those field lines, which is actually along the equipotential surface, if I move with displacements along the equipotential surface, I stay on the same potential. Potential does not change, right? I stay on the same potential if I manage to always move perpendicular to the field lines. Okay, so these are just some statements about the potential. We can actually see this based on the original definition of the potential difference. The original definition of potential difference, right? So delta V is potential difference. It's the potential difference between two places, place 1 and place 2. If we take the opposite of the net electric field, so this is the potential associated with this entire field, and imagine dot product with displacements that are taking me from position 1 to position 2, right? So this is one way to define this thing called the potential difference. But this potential difference, it's nice to imagine it as being the integral of a bunch of small changes, right? This is sort of a generic sort of calculus thing to say. And I'm imagining going from one place to another, where these are, in general, coordinates in three-dimensional space, where you imagine thinking about how the potential might change if you are imagining displacements that are this much, right? So these little displacements, if you imagine, these are calculus displacements, and they are vector valued. That is, there's a direction associated with them. So these dx's are just two places in space really close to each other, right? So this could be like place 1 and place 2. And this little vector is this little tiny calculus arrow. And I'm imagining taking the net electric field and dotting against a tiny calculus arrow to understand what's the difference in potential between these two nearby positions, right? They're nearby each other in an infinitesimal calculus sense. So if the electric field is, this symbol is perpendicular. So this means perpendicular. So if the electric field is perpendicular to the dx, then the dv is 0, because the dot product depends on the cosine of some angle, and it's the angle between one of the vectors and the other vector. And perpendicular means theta equals to 90, and the cosine of 90 degrees is 0, right? So there is no change in the potential if you pick positions that are organized relative to each other in a perpendicular sense to the electric field. So if these two positions were this way and the electric field was this way, that's an example of the dx vector being perpendicular to the electric field in the background, right? And that's what's happening up here. If you imagine, you've got positions that are close to each other, and as you move between them with a displacement vector, the electric field is perpendicular. So from here to here, there's no change in potential. But that's what equipotential means, right? No change. They're equal values at the two different locations. Okay, we can take sort of this analysis a little bit further, this analysis. So notice that dV will be negative. That is, there is a decrease in potential, right? This represents a decrease in the potential value. When, remember, dV is minus E dot dx. So if dx is in same direction as E, minus E dot dx will be negative. So if your displacement is in the same direction as the electric field, this small change in potential will be negative. That means it's a decrease. It's taking you from a high value to a low value. And that's what we see up here. The field lines are the direction in which the potential decreases. The field lines point from the high values of V to the low values of V, right? Okay, so I think you're, or I'm hoping that you can see some of this stuff make a lot of sense. So earlier I told you that I wanted to talk about equipotential surfaces, for example, these spheres of different potential, but also equipotential volumes. And that's what happens when you talk about conductors. Conductors have equipotential volumes. And the fast way to see that that's true is, here is a conductor, and inside of the meat of the conductor, what you're guaranteed that's special about conductors is that the electric field is 0 inside of conductors. So what this means is that for all of the various places inside of this conductor, these are all different places, right? For all of those various places, the potential is the same. So for every place P inside the conductor, E is 0. So whenever you calculate the potential difference between two places that are inside the conductor, you're going to do this. Right? So place 1 and place 2 are both inside the same conductor. So if they're both inside the same conductor, all you're going to do is anytime you do this integral, it's going to add up to 0. That doesn't mean, so careful, this does not mean v equals to 0. It just means v has the same value everywhere within the same conductor. It's absolutely true that you can take one conductor, right? So here is one lump of metal, and here is a different lump of metal. It could be that the one on the left is gold and the one on the right is copper, or they're both aluminum. Doesn't matter, right? They're just both conductors. And what's cool is we can start talking about what batteries do. So you know that a battery comes with a voltage. A typical AAA or AA battery is a 1.5 volt battery. And what this means is if you connect the conductor on the right to one end of it, called the negative end, and the conductor on the left to the other end, which is the positive end, what you get is this potential, say, of the left-hand side and the potential of the right-hand side. You don't know what their values are individually. What you do know is that the left-hand side is bigger than the right-hand side. The potential, the voltage of the left-hand side, that is every position inside of this conductor, has the same potential, and every position inside of this other conductor has the same different potential, and the difference between them is guaranteed to be 1.5 volts. That's what this battery does. Batteries maintain potential difference. They don't maintain a particular potential value for either conductor separately. What they do is they maintain a potential difference between two conductors. Okay, so I'm going to move on just a little bit further. So equipotential volumes also show up in non-conductor situations, right? So non-conductor situations. And the example, I have two examples. One is based on the shell theorem, right? So for the shell theorem, the idea is I have a uniformly charged sphere. I'll say that this sphere has a radius r and is charged with surface charge density sigma that's uniform. And so you know that q over 4 pi r squared is what sigma is, right? The charge of the shell is spread uniformly over the area of the sphere, 4 pi r squared, and that gives rise to the charge per unit area, called sigma. And the shell theorem, remember, says that if you ask what's the electric field inside, the electric field inside anywhere, right, here or here or here or at the dead center, the electric field is simply 0 everywhere. And this is not a conductor problem. It's actually, all you have to do is whatever material you have, sigma just needs to be uniform over the surface. That is, at this place, at this place, at this place, it has the same charge density, right? If you know that the charge is uniform over the surface, then you're guaranteed that everywhere you ask on the inside of the surface, the electric field will be zero. But the electric field on the outside is simply all of the charge divided by 4 pi r squared, points in the radial direction for the electric field vector, right? So if you go for radius values bigger than the shell's size, so that, for example, out here, then you're going to have an electric field. Right, and it does this kind of job. You know that if Q is positive, then the electric fields point radially away. But if Q is negative, then the electric field is going to point radially inwards, right? But that's handled by the sign of Q. So if Q is negative, the electric field is in the negative r hat direction, for example. But anyways, the electric field outside is not zero. The electric field outside is given by this formula, but the electric field inside is zero. And so if you look at the potential of this situation, let's imagine that we're studying the case where the charge is positive. Then what happens is, as a function of r, your potential behaves just like a point charge on the way in towards the sphere. But when you get to the sphere, the potential quits changing. That doesn't mean that the potential goes to zero. It just means it becomes constant. So that means that everywhere inside, right? Inside is a volume, and V is constant through that volume. So this is an equipotential volume, right? So everywhere within this sphere, it's all the same value of the potential. And it's actually equal to, it's just simply the potential at capital R this way. This right here is the value of the potential everywhere in here because it's the value of the potential at the surface, right? The value of the potential at the surface. Okay, so that was a non-conductor case, and there's one more non-conductor case that's interesting to point out, I think. In the case of infinite planes of charge, right? So in the Gauss's law chapter, you learned that if you study the electric field of a really, really broad, long, or, big, infinite flat plane of uniform charge density, what you get is that the electric field is constant. That's an important thing. If I have two of these planes, so let me finish my drawing really quick. So I have two identical, so same uniform charge density sigmas, and let's say that they're separated along the x-axis. So here's the positive x-axis out to the right, and that's the negative x-axis. They have uniform charge densities, so the electric field out here on the right-hand side of both planes is sigma over 2 epsilon naught I hat, right, in positive x direction. Let's say sigmas are positive. That's the electric field due to, say, this plane of charge. But this plane of charge, way over on this side, contributes exactly the same amount because the electric field is constant. So that means that the electric field is just sigma over epsilon naught I hat on this side. But way over here on this side, the electric field is sigma over epsilon naught, but in the opposite direction, so negative I hat. But in between, the electric field is 0. So what this is indicating to us is there's going to be all this volume from x equals to whatever this position is over to this position over here, right? Throughout all of this volume, the electric field is 0. And if the electric field is 0 there, then the potential does not change throughout this middle volume. And so it's suggesting to us a picture of the potential that looks like this. And in this case, we're talking about the potential as a function of x, independent of the y or z coordinates, because the y and the z are irrelevant in the infinite plane situation. But anyways, the potential is going to be some constant value between the two planes, right? So this position and this position on the x-axis. But remember that the electric field, which points this way on that side and this way on this side, right? So that these are the electric field lines. So the electric field lines point the direction to go down the potential. So the potential goes down like this on either side. So in the next video, I'm actually going to show you that this right here, this slope, right? This slope is related to E. It's related to the strength of the electric field. And the slope is related to the strength of the electric field over here as well. That is, E is the slope of V, right? Slope means derivative.